Welcome back to my channel, Campus Muneeb. Dear students, in today's video, I'm going to discuss this question number 25 of paper 1, variant 1, May-June 2024. Previously, I attempted this question in the form of a complete yearly paper on my YouTube channel. You can find the question of this answer, the answer to this question in this video, but there were some slight errors and mistakes in that question which I'm going to rectify in today's lecture, in today's video. So this is the question number 25. It states, structural isomerism and stereoisomerism should be taken into account when answering this question. The structure of the 3-methyl cyclobutene is shown, and this is the structure of the question. A mixture containing all the stereoisomerism of this compound is treated with HBr. This produces a mixture of isomeric bromomethyl cyclobutenes. How many stereoisomers of this compound have, and how many isomers of this compound are present in the compound mixture, in the product mixture? So basically we have to treat this compound in two ways. We have to check the stereoisomers when it is in its general form, and we have to check its isomers when it is treated with the HBr. So basically for this particular question, first of all, you should have a clear must have a clear concept of the stereoisomerism. In stereoisomerism, there are further two categories. There are two subclasses, you can say. The first is the optical isomerism, and the second one is the geometrical isomerism, or you can also call it as cis-trans isomerism. According to optical isomerism, it is this situation when an element, let's suppose if I take an example of carbon, it is bonded with 4 different atoms or group of atoms. Then this central carbon will be considered as a chiral center, and there is one chiral center, which means it will have 2 optical isomers. For every one chiral center, there are 2 optical isomers. And for cis-trans isomers, we should have a carbon-carbon double bond, and they must be bonded with atom or group of atoms which are similar on one side. They are similar on one side, but they are also different on one side. Like this X is different than Y, but there is also an X on the other carbon which is bonded through a double carbon bond. So this situation will be called as cis isomer. This is a cis isomer when the X's and Y's are on one side. This is the cis situation. And trans will be when either of the X and Y alternate their position. In this case, I can say that Y is positioned here and X is positioned here. So this will become trans isomer. So these are the basic concept which you should know before attempting this question. Now I'm going to discuss this relevant question, and we will apply this concept on this question. So here what we have to check how many stereoisomers are present in the given compound when it is in its actual form, 3-methyl cyclobutene. So for this purpose, I can also write this structure again, but in terms of all the carbon and hydrogen atoms. So this is called as its displayed formula. So basically it is like this one. We have carbon which are bonded double carbon bond, and then single carbon bonds are present here, and this is the methyl group which I can show like this, CH3. Now the carbons at these positions are bonded with 1 hydrogen atoms each at these positions, and there are 2 hydrogen atoms present at this carbon atom, and 1 hydrogen atom is bonded over here. Now this is the display structure of this compound. We have to check how many we have to check how many stereoisomers are present in this molecule, which means we have to check both the optical isomerism and cis-trans isomerism. The cis-trans isomerism or geometrical isomerism is not applied here. It is not applied because the structure is in its cyclic form, closed figure. It is, you can say, either cyclic form or a closed structure. In this case, there is no free rotation of these carbon atoms. They cannot freely rotate at this point because they are bonded with the other carbon atoms, which are further bonded into other carbon within the closed figure, so they are not able to freely move. Freely movement is restricted here. We can say it as like this. Free movement is restricted for carbon-carbon double bond. That's why cis-trans isomerism is not possible in this structure. Now we will check the other type of the isomerism, which is the optical isomerism. Now here in this structure we have to check which carbon atoms are bonded with different 4 different atoms or group of atoms. These two are not included because we can only have 3 atoms here: hydrogen, carbon and this carbon. So it is not possible to find the optical isomer in this carbon, not this one and not this one. So that's why we'll check the other carbon atoms here. Here in this case, this carbon is bonded with 2 similar atoms here, which are hydrogen. That's why this cannot be the chiral center, so it is also removed. Now the only carbon left in this case to check is the bottom right carbon. Now in bottom right carbon we have this structure. This carbon is bonded with 4 different groups. We have hydrogen here, we have methyl group here, and then we have this whole group moving from this direction and another group moving in this direction. Or if I take the example of this skeletal formula of the same compound, I will say that this carbon, which is circled here, it has 1 methyl group present, 1 hydrogen atom present here, and then we have a group of atom in this direction and another group of atom in this direction. They are different groups because the double bond is positioned at different positions. The double bond starts just at 1 bond distance if we go in this direction, and double bond starts at 2 position 1 and 2 when we move in this direction. So that's why we can say that this carbon is basically the chiral center here. This is the chiral center. So for every 1 chiral carbon we have 2 optical isomers. We have 2 optical isomers for this 1 carbon. So now here I will select the option A and B because these two options indicate the 2 optical isomers. So that's the right option from this column, 3-methyl cyclobutene. Now we have to check the isomers for the second column of bromomethyl cyclobutenes, and for bromomethyl cyclobutenes we have to consider the reaction between HBr and this compound. For this purpose I need to show you the notes or the literature, so I will show you my own AS chemistry notes. In my notes there is a topic of the addition of HX according to Markovnikov group addition reaction, or we can also say it as the stability of the primary cation, carbocation, stability of secondary carbocation, and stability of the tertiary carbocation. In this topic we covered how we can order the stability of primary, secondary and tertiary carbocations. Here we saw that when a molecule of HBr is basically added across the carbon-carbon double bond, then we will find this case that in one case the bromine will be added on the left of the carbon, and on the other case the bromine will be added on the right of the carbon, and it depends upon the stability of the carbocation. The major product is when we have the formation of the secondary carbocation, it will be the major product, and when it is bonded on the other carbon atom, then it will lead to the formation of primary carbocation, which is a minor product. So it is also referred to as Markovnikov rule or anti-Markovnikov rule. So basically this bromine can either bond on left of the carbon or it can be bonded on the right of the carbon, and we get two different products here. Now that will be applied on our given question. In our given question, we can have the same case. For this purpose, I am going to draw the skeletal formula of the same compound again. We have this compound and there is a methyl group present here. The HBr has to be added on this molecule, or I can add HBr over here. HBr will be added into this compound. Now this HBr, when added into this compound, then as a result of this, the double bond will be broken from this position. This double bond will be broken and a bromine will be added on one side of the carbon and hydrogen will be added on the other side of the carbon. Here in this case, there are the options, there are the possibilities that the bromine is added either to the left of the carbon or it is added on the right of the carbon. So we will get two different products in this case. I'm going to write these two products again in the skeletal form. So methyl group here and another product with methyl over here. Now if I say that a bromine is added on the left of the carbon of the double bond, then it will be bonded over here, and in the second case the bromine will be added on the right of the carbon, the right of the double bond, and the hydrogen atoms will be added in this way. Hydrogen will be added in this case over on the right side and it will be added on the left side of the right structure. Now it means that we have now different carbons on which we have to check the isomerism. It's stated here we have to check isomeric compound of this bromomethyl cyclobutane. Now this is called the bromomethyl. That's the name of this compound, bromomethyl cyclobutanes. It is in now you can see it is the plural form, which means we got two products here. Bromomethyl cyclobutanes, there are two products here. That's why it is in the plural form. We can say it as one. This is the first and this is the second molecule. Now we have to check the isomeric. Isomeric means we have to check stereo isomers, which includes both the geometrical and optical, and we have to also check the structural isomers here. These structural isomers. Now in this question, it means that we have to determine the isomers we have got here. The isomers, like the one which we checked before, included the cis-trans isomers. Cis-trans isomers will be discussed later on, and if we say about the optical isomer, then optical isomer will still exist at this point. In both the products, the optical isomer or the chiral center will be present at this point. because the rest of the other 3 carbon atoms will not contain the chiral center, as there are similar atoms or there are similar groups on the 2 sides of the carbon atom. Either if you check this one, then it means it has 2 hydrogen atoms on both sides. If you consider this carbon, then the group of atom on this direction and this direction are same, so there is no chiral center here, and there are 2 hydrogen atoms on this carbon. And if we check this one, then there are 2 hydrogen atoms on both sides of this carbon. And if we check this carbon, then the groups on both sides are the same, they are same. And for this carbon, the chiral center does exist here. There is another chiral center here, because if we move from this direction to another one, like if we move from this direction and if we move from this direction, these are different groups. So yes, one chiral center is additionally present at this point, and in my opinion, they should have included the optical isomer products in the answer as well. They should have optical isomers in the product, which in our question is not mentioned even according to the mark scheme and the examiner report. So let's see on which basis they have calculated the answer. I have to include one more topic over here, which is on the cis trans isomer of this type of the compound. For this purpose, I have to show you my notes. Now this is a page from my AS chemistry notes. In this page, we can see that if we have a closed figure which contains 4 carbon atoms, then there is a cis isomer and there is a trans isomer of the same compound, but we have to consider the 3 dimensions of the attached side groups as well. For the cis, we can see that it is a cis compound because the attached side group, which is the carboxylic acid in this case, it is coming out of the plane. This sign indicates out of plane direction of the side group, and in this case it is also the out of plane. So we can see that it is a cis compound because both the side groups are coming out of the plane. But here in this case it is a trans. It is trans because the group is going into the plane, because this direction and this is the direction of the bond when it is into the plane, and the other group, which is the wedge here, the wedge bond indicates it is coming out of the plane. So that's why it is a trans isomer. Now we have to apply the same rule in case of our question. So for this purpose, I'm going to write the products first when the hydrogen is bonded to the because it is the carbon number 1. When we start from here, it is carbon number 1, this is carbon number 2, this is 3. Now when the bromine is attached with carbon number 1, then the product which we will get will be, now this is the product when the bromine was attached on carbon number 1 at this point. But these bonds are basically in the 2-dimensional form, so I have to show this in the 3-dimensional form. So what I'm going to do is to raise these bonds as solid lines and change them into the wedged or dotted line. Let's suppose if it is the wedge, then it should also consider as a wedge bond. It means that both of these are coming out of the plane. When this happens, then we will say that this is the cis form of the isomer. This is a cis form. Now I have to draw another structure of this compound. Now this is the other other product, but now in this case I will change its direction and I will say that this time it is going into the plane instead of out of the plane. For this purpose I have to show this bond in the form of the dotted line. So this indicates that it is now going into the plane. When this is the case, when one bond is coming out of the plane and the other one is going into the plane, then this type of the isomer will be considered as a trans isomer. Now this is trans isomer, so now we have got two isomers here. This is the first one and this is the second one. Now I have to draw another product here. But this time the position of the bromine will be changed. I will, instead of putting bromine at carbon number 1, I will put bromine on carbon number 2 and hydrogen will come over here. Now this time I have to indicate the bond of the bromine, so I will say it is again a wedge at this point. Now both CH3 and Br are the bonds which are coming out of the plane, so it is now called a cis form of the product. Now I have to draw another product of this. So I can count this product as a third isomer. Now again I have the same product now, and as we showed the hydrogen atom at this position, now I'm going to show both of these bonds as the into the plane bonds. When they will become into the plane bonds, they will now again considered as cis products. Now these are the cis products because both the bonds are going into the plane. That's why now this is the fourth isomer. Now I am going to show another product here. In this case I will show that one of the bond is going into the plane and the other one is coming out of the plane. So for this CH3 I will show that it is going into the plane and the other one is coming out of the plane. The boron is coming out of the plane, so this will become the fifth isomer. And for the last product, now in this case I will, instead of showing for the CH2, I will show for the bromine that it is now going into the plane instead of coming out of the plane. Now that will become the sixth isomer. One more thing, these isomers are not cis. The fifth and sixth are not cis, instead they are trans. They are trans isomers, this one and this one. They are both trans isomers because one of the bond is coming out of the plane and the other one is coming in, is going into the plane. Now these are the six isomers. These are the six isomers which we got as a result of the reaction of the HBr with the given compound. This is the trans cis when it was bonded on the position number 1. This is the trans when bromine position on carbon number 1. And these four are the isomers when the bromine is positioned at carbon number 2. So that's how we get 6 isomers as a result of this reaction. But the thing which I want to mention here is that they did not include the optical isomer which should supposed to be present at this position. There was supposed to be optical isomers here, and they have not included those isomers in the mark scheme of the question. So that's how the question has been solved properly. And I want to add another thing here, that you can go through my Google Classroom for different resources which I have been frequently uploading at time to time. You can find solved topicals, you can find my workbooks, you can even find my my notes there. And I have also published my topical workbooks here, and you can find the screenshots, you can also find the video, and you can find my solved topical questions here. For example, here these are my solved topicals of different chapters. I have shown these screenshots of these solved topicals of the most chapter as well. You can find a lot of resources in my Google Classroom here. These are the solved topicals of the most chapter. I have done working on these solved topicals. So you can join my Google Classroom from the description of this video. I hope this question has clarified you. So the right answer of this question became in this question the number of isomers were 6 here. So that's why the right answer becomes B. B is the right answer. So that was all for today. I will meet again in another video with another question. You can leave any queries in the comment section on which I can make videos. So take care and bye bye everyone.